high-speed rail. When you hear that, you probably just think fast trains, right? But it's so much more than that. We're talking about this incredible symphony of engineering, civil, mechanical, electrical, all working in perfect harmony to basically tell the laws of physics who's boss. So let's get into it and peel back the layers on the amazing science that makes it all happen.
I mean, just look at this thing, 350 kilometers an hour. But the speed, that's almost the boring part. The real story is all the incredible science that's stopping this machine from, well, literally flying apart at the seams. Think about it. At that speed, everything wants to go wrong. It wants to jump the tracks, create sonic booms. The true marvel, the real magic, is the engineering that keeps it all together.
So where did this whole revolution even start? Well, for the modern era, you really have to go back to 1964. Japan, the Tokaido Shinkansen. This was the game changer. It was this huge moment that proved, for the very first time, that a train could actually go head-to-head with an airplane and win.
And just like that, the race was on. What's so wild when you look at this timeline is just how relentless the push for more speed has been. Japan sets the bar in '64, right? Then bam, France comes along with the TGV in '81 and just shatters that record. By the '90s, everyone in Europe is getting in on the action. But check out these test speeds. France hitting nearly 575 kilometers per hour on regular rails. And now you've got China's experimental maglevs blowing past 620. This isn't just a slow and steady improvement. No, this is a full-on aggressive assault on the limits of what's physically possible.
Okay, but to really get how these speeds are even achievable, we can't start with the train. Nope, we have to start with the ground underneath it. Because the big secret to going insanely fast is having an insanely stable path to run on.
Which leads to the obvious question, right? What's so wrong with the train tracks we've been using for like a century? Why can't a bullet train just use those?
And this slide just lays it out perfectly. Over here on the left, you've got your classic tracks, with the crushed rocks that's called ballast. And for normal trains, it's great. It's cheap, it absorbs vibrations. But once you start cranking up the speed past about 250 kilometers per hour, something crazy happens. The air pressure under the train gets so strong, it can literally pick up those rocks and turn them into tiny missiles. They call it ballast flight, and it is super dangerous. So the solution? Over here on the right, slab track. It's basically one giant solid piece of reinforced concrete. Yeah, it costs a fortune to build, but what you get is perfect geometric stability. No flying rocks, period.
All right, so we've got our unshakable path. Now we can actually talk about the machine that rides on it. We've got to look at the train itself. Because modern high-speed trains aren't just old trains with bigger engines. They've been completely reimagined from the ground up, and it really boils down to two key design philosophies.
First up, where do you put the engines? The old school way, right, was you have this massive, heavy locomotive at the front pulling a bunch of dead weight cars. But pretty much every modern bullet train uses something called distributed traction, and the idea is genius. Instead of one giant engine, you stick smaller motors under almost every single car. And the benefits, as you can see right here, are just huge. Your acceleration is off the charts because way more wheels are pushing the train forward, and you get way less wear and tear on the tracks because all that heavy engine weight is spread out. The bottom line is, spreading the power makes the whole system just better. Faster, more efficient, and easier on the infrastructure.
The second big decision is all about how you hook the carriages together. It's all about the bogies. That's the fancy word for the whole wheel setup underneath the train. And there are basically two main schools of thought. The French TGV, it uses what are called articulated bogies. See how one set of wheels is shared between two cars? Then you have the Japanese Shinkansen, where each car has its own two sets of wheels. And what's fascinating here is the trade-off you have to make. The articulated design is incredible for safety. If there's a derailment, it's way less likely to jackknife, fold up like an accordion. But the downside is you're locked into a fixed train length, which can be a pain for lining up with platform doors. The Shinkansen's approach is more flexible, which is great for busy stations, but you could argue that TGV design is safer if things go really, really wrong.
Okay, we have a super stable track, we have a brilliantly designed train. We should be good to go, right? Well, not exactly. Because as you start pushing past 300, 350 kilometers an hour, your biggest enemy isn't the friction on the rails anymore. It's the air. You are literally hitting a wall of air. And that invisible wall creates some very visible and very loud problems.
And the most dramatic example of this is a phenomenon called tunnel boom. The analogy here is perfect. Think of the tunnel as a cylinder and the train as a piston. When that train blasts into the tunnel at hundreds of kilometers an hour, it's ramming a column of air in front of it.
That air gets super compressed, and it has absolutely nowhere to go, except straight down the tunnel.
So here's the play-by-play. 1. The train's nose slams into the air, compressing it instantly. 2. This high-pressure wave shoots down the tunnel, moving at the speed of sound. And 3. When that wave hits the end of the tunnel, it just explodes out into the open. And I mean explodes. It creates a massive boom, loud enough to shake buildings and scare the daylights out of anyone living nearby.
So how on earth do you solve a problem like that? Well, with a really elegant two-pronged attack. First, you deal with the train itself. Instead of a blunt nose that smacks the air, engineers design these incredibly long aerodynamic noses. We're talking up to 15 meters long. They're designed to slice through the air, displacing it gently instead of all at once. Then, for part 2, you modify the tunnels. They add these special hoods at the entrance with vents or slits in them. As the pressure wave builds, these vents let some of the air bleed out, which breaks up that one giant scary shock wave into a bunch of smaller, weaker ones that are basically harmless.
Okay, we've dealt with the track, we've dealt with the air, but we haven't talked about power. These things are all electric, and they are thirsty. A single train can draw up to 15 megawatts of power. That is a ton. So the next giant puzzle is, how do you feed that much electricity to something that's moving at like 90 meters per second?
Just to give you an idea of the forces we're dealing with, look at this number, 54,000 newtons. That is the constant tension that the Japanese Shinkansen has to maintain on its overhead power line. That's like hanging a multi-ton weight from it. The question is, why? Why does it have to be so incredibly tight?
And the why is all about this fantastic analogy, a plucked guitar string. So the arm on top of the train that touches the wire is called a pantograph. As it speeds along, it creates a little wave that travels down the wire, just like when you pluck a string. Now here's the dangerous part. If the train's speed starts to match the speed of that little wave, you get resonance. The wire starts whipping up and down violently. The pantograph can lose contact, and you get these huge, destructive electrical arcs. It's a total disaster. The only way to prevent this is to make sure that wave always travels faster than the train. And how do you make a wave travel faster down a string? You crank up the tension a lot.
So we've gone deep into the weeds on the engineering, which is just amazing. But let's zoom back out. What is the actual impact of all this technology? Because it's about way more than just getting from point A to point B faster. It actually changes how we live, how our economies work, and how we treat the planet.
And let's start with the big one, the environment. I mean, this chart really says it all. It's not even a close call. On a per-person basis, high-speed rail is just dramatically cleaner than cars, and it absolutely crushes airplanes. And get this, if you're in a country with a pretty clean electrical grid, swapping a short flight for a train trip can slash the carbon footprint of that journey by up to 97%. Let that sink in. This isn't just a small improvement. It is one of the single most powerful tools we have to clean up our transportation sector.
Now, the economic side of things, that's a bit more of a double-edged sword. On the one hand, you can get what's called the diffusion effect. You connect a smaller city to a big one and you can spread the love. Wealth, jobs, investment flows outward. But there's a flip side. You can also get the siphon effect, where that super fast train acts like a giant vacuum, sucking all the talented people, the money, and the opportunities out of the small town and into the metropolis. Which one you get really comes down to whether you have smart policies and planning in place to manage it.
But here's the thing. For all of its incredible success, the basic idea of a steel wheel rolling on a steel rail, it's starting to hit a wall, a physical limit. The friction, the maintenance, the sheer amount of power you need, it all goes up exponentially as you try to go faster. So if we want to break the next speed barrier, we can't just improve the current tech. We have to change the game entirely.
And this is what's next. First up is maglev, magnetic levitation. You get rid of the wheels altogether and use powerful magnets to make the train float. No friction. Japan's already hit over 600 kilometers an hour with this. But the real holy grail, the ultimate endgame, is evacuated tube transport. You take a maglev train and you put it inside a tube with almost all the air sucked out. So now you have no wheel friction and no air resistance. And the speeds they're talking about are just mind-bending. China's T-Flight project, they're aiming for 1,000 kilometers per hour. That's faster than the plane you'd take on vacation.
So that leaves us with a pretty profound question to think about. For more than half a century, the story of high-speed rail has been this epic battle against two fundamental forces, the friction of the rails and the resistance of the air. We've just about conquered them. So what happens? What does our world look like when we finally eliminate both of them entirely?